This video is about the ideal gas law, and we're going to start by looking at the three gas laws to see where the ideal gas law comes from. So the first gas law that we're going to talk about is called Charles' law, and it's named after Jacques Charles, who discovered it in the 1780s. So what he discovered was that the volume of a fixed mass of gas is directly proportional to its absolute temperature if the pressure is constant. So we can also write that as V proportional to T, or we could say that V over T is equal to a constant. And we can see how this works by looking at the simulation. So the pressure has to be constant, so set the pressure to constant. And now we can change the temperature and see how the volume is affected. So I'm going to add some heat, and we can see that the pressure stays the same and the volume is increasing in order to keep the pressure the same. So we can see that when temperature increases, the volume increases, which agrees with our formula that V is proportional to T. And then if we remove some heat, we're cooling it down. So we're lowering the temperature, and that means that the volume is decreasing in order to keep the pressure constant. So it kind of makes sense using the simulation. The next gas law is called Boyle's law. And this one is named after Robert Boyle, who discovered it in the 1660s. So it was a bit earlier than Charles' law. And Boyle discovered that the volume of a fixed mass of gas is inversely proportional to its pressure if the temperature is constant. So this time it's inversely proportional. So we can try this with the simulation as well. And we can see that we can't really change the pressure in the simulation, but what we can do is change the volume and see whether the pressure is inversely proportional to it. So if I increase the volume, then we should get that the pressure decreases. So let's try it. If I increase the volume, yeah, you can see that the pressure decreased on the scale. And if I decrease the volume again, we should see the pressure increasing. Yeah. And you see that the temperature stays constant by adding or removing heat here at the bottom, just because we're saying that the temperature has to be constant for this law to work. Okay, we could also write that as V is proportional to 1 over P, or we could say that PV is equal to a constant. Right, the third and last gas law that we're going to talk about is the pressure law. So this one doesn't actually have a name after anyone, but it's just called the pressure law. And it was discovered in around 1700. And it states that the pressure of a fixed mass of gas is directly proportional to its absolute temperature if its volume is constant. So now we're going to set this third parameter to constant, which is the volume. And that means that we can't change the volume of this. We can only change the temperature, and then we can measure the pressure. So if I increase the temperature of this, we should see the pressure increase. Yeah, so the pressure is increasing. And if we decrease the temperature, then the pressure decreases. So pressure is proportional to T. And we could also say that P over T is equal to a constant. So let's see what happens if we combine all of these three gas laws. So we'll first write them down again. So Charles' law was that V over T is constant. Boyle's law was that PV was equal to a constant. And finally the pressure law was that P over T is equal to a constant. So it's a bit tricky to combine all of these, but one thing we could do is to multiply them by each other. So we've got three equations. We can multiply the left-hand side by each other and the right-hand side by each other. So on the left-hand side, we're going to get V over T times PV times P over T. And on the right-hand side, we're going to have a constant times a different constant times a third constant. And we're not going to worry about the values. We're just going to call that a new constant. So we'll just write constant on the right-hand side. And then we'll simplify things on the left, which gives us P squared V squared over T squared. And on the right, we still have just a constant. And now, because they're all squared, we could take the square root, because they're all positive values. We can't have a negative volume, we can't have a negative pressure, and we can't have a negative temperature because it's in kelvins. So that means that we can take the square root of both sides, and on the left hand side we're going to have PV over T, and on the right hand side we're still going to have a constant. It's going to be the square root of the constant that we had before, but that still makes a constant. So what is this constant then? Well, Avogadro had a hypothesis, which was that the volume of a gas is proportional to how many moles of the gas, or how many molecules of the gas there are, if we're keeping the pressure and the temperature constant. So that kind of makes sense, because if we have more gas, they're going to want more space in order to keep the same distance between them. So what that means is that we can split our constant into n, the number of moles, times a different constant. So again, we're changing what the constant is, but it's still not going to matter. So we'll write PV over T equals n times constant. So we're still stuck with a constant there, aren't we? But we can resolve that by just calling this constant something, and we're going to call it R. R is the gas constant, and we'll write down the value of it in a second. But first, we'll write out the equation with this R in it. So if we multiply both sides by T, just to make sure we don't have any fractions, then on the left hand side we just get PV, and on the right hand side we get nRT. And this is finally the ideal gas law. PV equals nRT. And we could also call it the equation of state of an ideal gas, because it describes all the different states that the ideal gas can be in. So I don't mean phases now, I mean states. So different pressures, temperatures and volumes that we can have the gas in. So now let's write down the value of R. So if we didn't know the value of R already, we could measure it in the lab. If we just rearrange the equation, we get that R is PV over NT. So if we have a gas where we can measure the pressure and the volume and the temperature, and if we know how many moles of the gas there are, then we can just take all those measurements and calculate the constant R. But this has already been done for us, and we know that the gas constant is equal to 8.31. And now we're going to have to do some units. So pressure is in newtons per meter squared. Volume is in meters cubed. N is number of moles, which is just in mole, and because it's in the denominator, we call it mole to the minus 1. And temperature is in Kelvin, so we get a Kelvin to the minus 1. And let's see if anything cancels here. We got m to the minus 2, and then we've got m cubed. So that means that we're going to have newtons times meters, and newton times meters makes joules. So let's shorten all of that. So we got joules per mole per Kelvin, and that's the unit of the gas constant. And this value is given in your formula booklet, so you don't need to know it. And the same is true for the ideal gas law, it's also given in the formula booklet.